Hello everyone, I am Sandeep Prakash Metalkar and you are watching Sandy's Desk.
The main discussion for this class is anisotropic interactions and TPS processes. Before going into this one, we shall see what is a tensor. When people first hear the term tensor, a reasonably high percent of them have the same question: what is a tensor? At least after the end of this class, a few things about, I hope, a few things about tensors will be clear to you. For better understanding tensors, I would not like to approach this problem in a conventional way of using a bunch of mathematical equations, but instead use some simple objects made up of thermocol. Okay, some some arrows, some small piece of thermocol. So these can be considered as unit vectors. Okay. So in order to better understand tensors, you have to have a solid understanding what a vector is actually. Okay. If you have taken any PU level physics course or college level physics course, you would probably think of vector as something like this: an arrow representing a quantity that has both magnitude as well as direction. That is both magnitude and direction. Okay. So this could represent like this one, an arrow representing both magnitude and direction. So wherein the length of the arrow is proportional to the magnitude of the quantity, and direction of the arrow tells you the orientation, or orientation of the arrow tells you the direction of the quantity. Okay. So this could represent force of gravity acting on object. For example, Earth is there. So you have any object. So force of gravity is acting on the object. Force is a vector quantity. So direction is this one and it has some magnitude. Or strength and direction of the magnetic field. Or in a flowing fluid, if you have a particle in a flowing fluid, it can vector can represent the direction and magnitude of the particle in a flowing fluid. Okay. Not just this, these are some of the common examples. Vector can represent other things as well, like area. Is area vector? Area of anything, area of a square, rectangle, like it is area vector? Huh? Is area vector? No. Area is a vector actually. Let's see how. Suppose you have an area like square. Suppose this is x direction, this is y direction. Okay. So how can vector represent area? Simple. You simply make the length of the arrow proportional to the amount of the area. Okay. And make the direction of the arrow perpendicular to the surface. So in this way, vector can represent an area. See, this length of the arrow should be proportional to the area, and direction of the arrow should be normal to the surface. Normal means perpendicular to the surface. Let's see how. Suppose we shall choose two length vectors. So this is suppose say y direction. Suppose say this is x direction. And let's choose two length vectors of length say 6 centimeters or any random value. 6 centimeters. This is also 6 centimeters. That means this is 6 centimeters. This is also 6 centimeters. Okay. So we know that vectors can be multiplied in two ways. How? Dot product or cross product. product of two vectors, say A dot B, gives some scalar quantity, whereas a cross product of two vectors in turn gives a vector. Okay? And the length of the dot product is given by the formula A dot B is equal to magnitude of A, magnitude of B, cos theta. Okay? Theta is the angle that two vectors makes between them. Okay? And the length of the cross product is given by A, magnitude of B, sin theta, and a unit vector n. Okay? Because cross product gives a vector, scalar product gives a scalar. See, easy direction is not important. Here, the result in answer, but whatever answer we get, that also has a direction. And this n should be perpendicular to both A as well as B. Okay? See, if you increase or if you double A here, then the length of the dot product also doubles. Or if you half any one here, then the length of the dot product is half. That means it is directly proportional. Okay? Here also, if you double A, cross product doubles. If you half A or AB, the cross product is half. Okay? And we know that cos theta varies as if cos 0, 90 and 180 if you take, cos 0 is 1, cos 90 is 0, cos 180 is minus 1. And sin theta varies as 0, 90 and 180. Sin 0 is 0, sin 90 is, sin 180 is 0. That means see, if angle this theta is 0, then cos theta is 1. If theta is 90, then this whole value becomes 0. Okay? That means a dot product is a measure of how parallel the two vectors are. Or a dot product is maximized if the two vectors are parallel to each other. Okay? That means dot product is a measure of how parallel the two vectors are. Okay? Sin theta, see, for sin theta, sin 90 is 1. That means cross product is maximized when the two vectors are perpendicular to each other. Or in other words, a cross product is a measure of how perpendicular the two vectors are. Okay? So here we need not worry about the direction. Here we need to worry about the direction. What is the direction of A cross B? Giving you A, B, sin theta and 1. See, n should be perpendicular to A, also n should be perpendicular to B. So how to get the direction of cross product? See, if suppose there are two vectors A and B. So making some angle theta say. So align your right hand along the first vector now A. Okay. Slowly move towards the second vector B. So the direction in which your thumb points is the direction of the cross product. It need not be the same. A cross B, if you do, the direction will be like this. But if you do B cross A, the direction will be opposite. Okay. So remember that cross product gives you magnitude as well as direction, whereas the dot product gives you only magnitude. Okay. See, we were concerned about this one, right? This area. So let's choose to multiply these two vectors. First in terms of dot product. First we'll take the dot product. Second we'll take the cross product. Let's see which gives us satisfactory answer. First we'll do the dot product. Suppose this is a x unit vector, or you can say 6i, where I is the unit vector. Unit vector means it has a length of 1. Okay. And this is another unit vector 6 say j, or simply you can say 6x or 6y. Okay. So and suppose that this is a vector, this is b vector, this is a, this is b. So a dot b gives you what? 6i 6j cos theta, that is 36 ij cos 90, or this is 36, it is nothing but cos 90 is 0, dot product is giving you answer as 0. Okay. So now let's try dot cross product. A cross B is equal to 6i into 6j sin theta, that is 6i or 36 ij multiply cross product ಮಾಡಿದ್ರೆ the resultant should be such that it should be perpendicular to both I and j, that is k cap, like that k cap is perpendicular to both I and j. Sin 90 is 1, that is 36 k cap. So a cross product is giving you the known value of area. Everybody knows that area is 36, length into breadth. Okay, so the cross product is giving you the known value of area. In addition, what it is giving you is direction, that is perpendicular to the plane of which the area is determined. So this vector is perpendicular to both this as well as this vector. Okay. So in this, that means an area or a surface like an area can be best represented in terms of vector rather than scalar. So I hope ಇದು ವೆಕ್ಟರ್ ಅಂತ ಕನ್ಸಿಡರ್ ಮಾಡಲಿಕ್ಕೆ ನಿಮಗೆ ಏನು ತೊಂದರೆ ಇಲ್ಲ. This is vector, length is a vector, it has direction, ಇದು vector. So the resultant should be also vector. So how is area a vector and why do we need such representations? Or why do we need to represent area as vector? Suppose say this is a three-dimensional space. X, Y and Z. And suppose say there is a two-dimensional space within that one. This is a two-dimensional subspace. Let it be A vector, let it be B vector. So how is area a vector? This is more of a maths question. Okay, this is a peculiar problem in three-dimensional space. In a three-dimensional space, an area such as a plane is a two-dimensional subspace. Okay, see, imagine, see, you have a piece of paper. Say, if you have a piece of a paper and you keep that at the bottom and stand on the piece of the paper. Okay, the direction in which your head points will always be a way to know how the paper is oriented in three-dimensional space. Okay. This is for, see, if you stand, this is a paper and you stand on the paper. Okay, so the way in your, the direction in which your head points will always be a way to know how this plane is oriented in three-dimensional space. Okay, this is called as a normal vector to this plane. So its direction is perpendicular to this plane. Okay, so if you now consider the convention to have the length of this normal vector proportional to the area of this vector. Suppose it is 36 square centimeters is there. Suppose you make the convention that the length of this vector is proportional to 36. So then this vector can give you the complete information about this two-dimensional subspace. How it is oriented in three-dimensional space, the vector part, and how big the vector is, how big the area is. How big the area is proportional to how much is the length of the vector. So this gives you the complete description of two-dimensional space, right? So in this way, a vector can represent area as well, other than what we know. Okay, area is a vector as opposed to scalar. See, vectors can represent lot of other things. So beyond just thinking of vectors as representing quantities with both magnitude as well as direction, to coming to the terms that vectors are just the members of wider class of objects called tensors. You have to have a solid understanding about vector components and basis vectors. Basis vectors are nothing but unit vectors. Okay. And in order to think about vector components, it is better we have the model of the coordinate system. The simplest coordinate system is Cartesian coordinate system. So Cartesian coordinate system has three coordinates: x-axis, y-axis, and z-axis, and all are meeting at right angles to each other. Okay. For example, this can represent a Cartesian coordinate system. Okay, imagine that this is x-axis, this is y-axis, and this is z-axis. So for reference, I will write the same thing on a board as well. This is x-axis, this is y-axis, and this is z-axis. And one thing to remember about Cartesian coordinate system is that it always comes along with basis vectors. Basis vectors means unit vectors. And one thing to remember about unit vectors is it has the length of 1 of whatever the units of vectors are. See, unit vectors in length anything, it is 1. Suppose the vector is 8 meters, then unit vector is 1 meter. Suppose the vector is 8 centimeter, unit vector is 1 centimeter. Its length is always 1. Okay, so this can represent a, for example, this can represent a x unit vector. Okay, see, E x directional. See, suppose this length is 10 centimeter. So this vector is made up of 10 unit vectors. Okay, so like this, one unit hanging. And the direction of the unit vector is always along the direction of its coordinate x-axis. So this can represent a, for example, x unit vector. If I place this one here, over here, it is a x unit vector. So this can I can represent it as x with a little hat over it. This can be a x unit vector, or simply I can also represent it as I with a little hat over it. Okay. Or for example, another one. So this can represent a y unit vector. So if I place it along this axis, this is a y unit vector. So or this one, this itself if I place here, it is a y unit vector. Or this if I place here, it is a z unit vector because it always has a length of 1. So y unit vector I can represent as y with a little hat over it, or j. Similarly, z I can represent as z or k. So once you have the Cartesian coordinate system and unit vector in place, now we are in a position to find the component of a vector. Suppose this is a vector of our interest. This is a vector. Okay. So we need to find component of the vector. What is the component of a vector? See, suppose this vector is oriented this way. It will have x component, y component as well as z component. So it will be easy for us to visualize vector component if we just restrict our discussion to only xy plane or xz plane, only two dimensional. Z component is not. It has only x component and y component. It has no z component. Suppose to make things easy, I will just imagine that this vector is a line in xy plane. Okay. Now I need to find the component of this vector. And how can I find the component of this vector? Simplest way. I have to project this vector on x-axis, and I have to project this vector on y-axis. So that will be x component, y component. What is the simplest way to do that? No, I am not using any mathematics here. Simplest way, common sense. See, darken the room. Okay, there should be no light source, and use the light source to project this vector on x component. So if I imagine that a room is dark and I have put a lamp source here. Okay. the point at which its shadow falls, that will be x component. Okay, and if I have to find the y component, so I place a light source here, and the point where the shadow of this vector falls, that will be y component. Simple as that. Okay, now. So suppose say I am putting the light source here, okay, and I get a reflection or shadow till here. That means it will be, this pixel is the x component. Suppose I see this is angle theta. Okay, suppose I make the angle, I increase the angle with respect to x-axis, then the shadow will come here. That means x component has decreased. Okay. Suppose if I make this arrow fall exactly on x-axis, then what? The length of the arrow itself is x component. Okay. So same thing. If I am going to change the angle, the x component will increase or decrease. Same thing can happen with y component. Okay. Or so this is a rudimentary way of explaining a vector component. So if I have to represent it, I have to use some mathematics, at least basic mathematics. So another way of visualizing vector component is that in going from base to tip of the vector, how far do I have to go along x-axis and how far do I have to go along y-axis? Okay. Or how many x unit vectors I need and how many y unit vectors I need from going from base to tip of the vector. So I can show you this. If I see, suppose imagine that these are all unit vectors and there is a little gap for it. Arrow is just a direction in enter. So imagine that little gap in enter. Okay. So that means 1, 2, 3, 4, and say 5. So this vector is made up of 5 x unit vectors. Okay, and in a y-axis 1, 2, 3, and 4. So that means this particular vector is just E vector here. This vector is made up of 1, 2, 3, 4, 5 x unit vectors and 1, 2, 3, 4 y unit vectors. So to represent that vector, I can use that vector is made up of 5 x unit vectors and 4 y unit vectors. Okay. This is a perfect valid representation of that vector. Okay. So in order to complete the picture, since there is no z component, I can simply write this one as 0 z component, or I can simply write 5i, 4j, and 0 k. So that means this is a perfectly valid representation of that vector. So instead of using an arrow to represent this vector or drawing an arrow to represent that vector, I can simply represent this one as 5. That vector is made up of 5 x component, 4 y component, and 0 z component. Okay. Suppose if this vector is aligned like this, okay, then it will have z component also. So use the shadow where it falls. If it falls here, this is the x component. Shadow, use the shadow. If it falls here, it is the y component, and z component will also be there. But to make things easy, I have ignored the z component. But that doesn't mean z component is not. Or if you know, or if you exactly know what the unit vector is, you even don't need this one, this representation. So, because we know that unit vectors are having a length of 1 of whatever the unit of vectors are. So that means we do not need this representation as well. So if you are having the perfectly valid or perfectly good knowledge of what a unit vector is, you can simply write the vector as 540 and put a nice parenthesis over that. So this looks like a row matrix or column matrix. 5, 4, 0. So this is a vector. Okay. So but this representation pertains only to the vector we have lying on the table. This is not a general representation. In order to represent a general vector, what we can do? For example, there is a vector A. What we can represent? It is made up of something x component, it is made up of something y component, it is made up of something z component. So generally we can represent vectors as something like this. Of course, Ax pertains to only x unit vector, AY pertains to only Y unit vector. AZ pertains to only Z unit vector. ಅಂದ್ರೆ ಎಷ್ಟು X unit vector ಇದೆ, ಎಷ್ಟು Y unit vector ಇದೆ, ಎಷ್ಟು Z unit vector ಇದೆ. This is how the vectors can be represented. ಹೌದಲ್ಲ? Notice that you have only one index per component. This is a component. So you have only one index per component. ಹೌದಲ್ಲ? So that means there is only one directional indicator. We need only one directional indicator. X direction, Y direction, or Z direction. This is what makes vectors tensors of rank 1. Because there is only one directional indicator. Okay? One directional indicator per component, or one basis vector, or one unit vector per component. One basis vector per component. Okay. This is what makes vectors tensors of rank 1. By the same logic, scalar should be tensors of rank 0 because there is no direction indicator. Okay. I will tell you in a minute why it is so powerful to represent tensors as a combination of components and basis vector. So tensors are always represented as a combination of, see here, is a component, is a basis vector. Okay? That I'll tell you in a minute, but I want to show you an example of higher rank tensor, tensors of rank 2 or rank 2 tensor. So rank see, ಇದು rank 1 tensor. Rank 2 tensor is scalar. Scalar मतलब pure number, something random number x 2 3. It is scalar. Okay, ಇದು vector. So rank 2 tensor ಹೇಗಿರಬೇಕು? Rank 2 tensor represent ಮಾಡಲಿಕ್ಕೆ ನಮಗೆ ಎಷ್ಟು components ಬೇಕು ಮತ್ತು ಎಷ್ಟು basis vector ಬೇಕು? 2 basis vector. And how many components? We would need 9 components to represent. ಹೇಗೆ suppose a x x, a x y, a x z, a y x, a y y, a y z, a z x, a z y, a z z. So this is an example of rank 2 tensor. Okay. So notice that instead of 3 components and 3 basis vectors or 3 unit vectors, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 components now. 9 components and 9 sets of 2 basis vectors. Okay, these are basis vectors or direction indicators, right? So here rank 2 tensor has 9 components and 2 basis vectors per component. That means there are 2 directional indicators. But why do we need such a representation? That is the question. Why do we need such a representation? There can be even rank 3 tensor. Rank 3 tensor ಅಲ್ಲಿ ಎಷ್ಟು components ಇರ್ತದೆ? Rank 3 has 27 components and each component has 3 basis vectors. So but why do we need such a representation? So imagine that so you have a box, correctly perfectly cubical box, okay? And there is a force acting inside the box, or imagine that some bomb is placed or something explosive is placed. Okay, when the explosive explodes, it will explode in all possible directions. One direction will explode, x direction will explode. That means whatever force the explosion is making will have components along x axis, y axis, and z axis. And we have already seen that plane is a or area is a vector. Suppose imagine that we have a object like a box and there are forces acting inside the box. So imagine there is a perfectly cubical box. Inside that box there might be surfaces. For example, this is a box. Okay, and something this one. See, this is one area, right? It one area. This is another area. This is another area. This is another area. Okay, there are many areas there. So inside the box, there are surfaces whose area vectors point along x-axis, y-axis, or z-axis. So we have the coordinate system, right? Okay. Same coordinate system. This is x-axis, this is y-axis, and this is z-axis. See, this is x-axis. So this area vector, or suppose say this area vector points along x-axis. Okay, this area vector points along y-axis, and this area vector points along z-axis. Same, ಇದು z-axis point ಆಗ್ತಾರೆ, up or down, no worries. Okay, ಈ area ಇದೆಲ್ಲ ಇದು y-axis point ಆಗ್ತಿದೆ, and this area vector points along x-axis. ಅಂದ್ರೆ x direction see, suppose e vector and e vector multiply ಮಾಡಿದ್ರೆ you will be getting a normal vector ಅಲ್ಲ, ಅದು x direction point ಆಗ್ತದೆ. There are how many? There are surfaces whose area vectors point along x axis, y axis, or z axis. So on each of these surfaces or area there might be a force whose component is along x axis, y axis, or z axis. Okay na? See, suppose ಇದು ax component ಇದೆಯಲ್ಲ, area vector point along x axis, that is ay component whose area vector point along y axis, that is az component whose area vector point along z axis, and on each of these surfaces there might be a force which has a component along x axis, y axis, or z axis. For example, axx might represent a force whose area vector point along x axis. Axx represents the force whose force is in x direction and area vector points along x direction. Or axy might represent this component whose area vector whose force is around y direction plus area vector is around x direction. Or axz might represent a force whose area vector point along x direction but force is along z direction. ಹೌದಲ್ಲ? ಇಷ್ಟೇ ಸಾಕಾಗಲ್ಲ. ಈಗ just now area x consider ಮಾಡಿದ್ರೆ there are area whose vector point along y direction. So this representation also we need ayx, ayy, ayz, or this also we need azx, azy, azz. Are you understanding my point? See, area is a vector. Okay, so there are how many? This is a three-dimensional space now. So there are areas here or surfaces here whose area vector point along x direction, y direction, or z direction, and there might be a force, so which might have x directional force whose area vector point along x direction, or y directional force whose area vector point along y direction, or z directional force whose area vector point along z direction. Or y directional force whose area vector point along x direction, z directional force whose area vector point along x direction. So in order to completely characterize all the possible forces on all the possible surfaces, you need 9 components and 9 sets of 2 basis vector, because there are 2 directional indicators here. One is area vector, one is force. Suppose there are 3 directional indicators, then you will need 27 components and 3 sets of basis vectors per component. It is an example of higher rank tensor, but for our discussion for G we need a second rank tensor. So I hope you have got an idea what a tensor is and why we need such a representation, right? So this is an example of rank 2 tensor. Thank you for your patience.